Okay, today we will do electric field due to an infinitely long, straight, uniformly charged wire. For example, like we have seen in this diagram, we have a very long, thin, straight, uniformly charged wire here. Okay, this one. So what is our aim is to find out the electric field. For example, let us say at some point, let us say point P here, which is at the distance r from the center of the wire. One more thing we have to remember here is that we will use or it is the application of Gauss law. Okay, so let us start writing it. Now consider an infinitely long, thin, straight, wire with uniform linear charge density lambda. So lambda will be the charge per unit length. Lambda will be the charge per unit length. Okay, now let us write about P. Let P be a point. Let P be a point at a distance r from the wire, and E be the electric field, at point P. Okay, so we have here what we have. We consider point P, which is at the distance r from the wire, and also let us say suppose E will be the electric field at point P. Now what we are going to do is to calculate E. Okay, now to calculate, let us write next line. To calculate the electric field, we consider a cylindrical Gaussian surface. So since we have to apply the Gauss law, what we have to do is that we have to write what we call Gaussian, or we have to draw what we call Gaussian surface. Okay, so we consider a cylindrical Gaussian surface as shown in the figure 1. Okay, so here in this figure we have the Gaussian surface. This dotted line here in the form of cylinder, it represents the Gaussian surface. Okay, so let us continue. Since the electric field is everywhere, radial, okay, flux through the two ends of the cylindrical Gaussian surface is 0. Okay, so since here you see the flux through, let us say the electric field here is, in this diagram, the electric field is everywhere radial. That means it is along the normal to the curved surface of the cylinder, what we have is the flux through the two ends of the cylinder, that is this side and this side, it will be equal to 0. Okay, so let us write about the curved part now. At the cylindrical part, of the quiescent surface, E is normal to the surface. E is normal to the surface at every point and its magnitude is constant. So if we look at the curved part of the cylindrical quiescent surface here, let us say if we have like that, then this side and this part of the cylindrical surface, we could see that E is always normal to the surface and the magnitude of E is constant everywhere. Okay, since it depends, let us write some more. Since it depends only on R. Since it depends only on R. Okay, so the surface area, of the curved part is twice pi RL. Okay, where L is the length, of the cylinder, and R is the radius, of the cylinder. Okay, so R is the radius of the cylinder. Now consider a very small area element, area ds, okay, on the quiescent surface, okay. E and ds are along the same direction. Okay. Now the electric flux through curved surface is equal to integration over a closed surface E ds cos theta, which is equal to integration over a closed surface E ds. Since here theta is equal to 0 degree, okay, so cos theta will be equal to cos 0 degree, which will be equal to 1. Okay, now then, okay, let us, E is constant everywhere, the magnitude of the electric field is constant everywhere on the quiescent surface, so we take it out. E then integration of ds. Okay, so it will be equal to E into integration of ds is a small area element, so if we add all the small area element, we will get the total area of the curved surface. So it will be twice pi RL. Name this as equation number 1. So in E into twice pi RL. Okay, now let us continue here. Now flux through the Gaussian surface, let us say it is phi. Flux through the Gaussian surface, which is phi, is equal to flux through the curved surface. Okay, or we can write here phi, it will be equal to E into twice pi RL. Okay, name this as equation number 2. The net charge enclosed by Gaussian surface is, okay, let us write here, Q will be equal to lambda L. Lambda is the charge per unit length and L is the length, so it will be the total charge will be lambda L. Now therefore we can write here by Gauss law, okay. So we have phi, it will be equal to Q by epsilon naught, so it will be equal to lambda L by epsilon naught. Name this as equation number 3. From equations 2 and 3, okay, we have, from equation 2 and 3 we have, okay, phi will be equal to E into twice pi RL, which is equal to lambda L by epsilon naught, or E, it will be equal to lambda L by twice pi epsilon naught RL. Okay, L and L get cancel. You will have, or E, it will be equal to lambda by twice pi epsilon naught R. Name this as equation number 4, and this is the required equation. Now we can write it in vector form, so let us write it vectorially in vector form. Okay, E at any point is given by E, which is equal to lambda by twice pi epsilon naught R, and then a unit vector n cap here. Okay, so name this as equation number 5. So equation 5 will give the value of E in vector form at point P. Okay, now where, let's write something about unit vector. So where n cap is the radial unit vector, in the plane normal to the wire passing through the point P, passing through the point. So in this case, passing through the point P. Okay, E is directed outward if lambda is positive and inwards if lambda is negative. Okay, so with this we complete the topic today. Thank you.